Hi guys, my name is Paul Rodriguez. I work here at SDSC. I do a lot of the support on Exceed. Today we're going to go into deep learning, and we're going to start with, let me go ahead and just go to the next slide and do the outline. I'm going to start with an overview of neural networks, introduce convolution neural networks, and we're going to talk about introduce Keras and talk about how you go about some of your steps for building networks in Keras. And we'll do an exercise. So we'll do about, I think, 45, 50 minutes, and then an exercise for maybe half an hour, and then we'll do another short, some more slides for maybe 10, 15 minutes, and then another exercise. So that's how I'm going to break up this first part. And then Mai's going to talk about, I think you do transfer learning today, Mai, or is it?
This afternoon. So transfer learning and layers is this afternoon.
Okay.
I'm not this afternoon, the second part of it, whenever that starts.
Let's call it the second part, because I guess depending on where you are, it could be afternoon or morning.
Yeah.
Okay. So that's what we're doing this first part and second part. So I always like to start, and I'm going to start with just sort of a broad introduction to neural networks, and it's going to be, there's really a lot one can say, but this is going to be, I think, hopefully build up some intuition. So I always start with thinking about it from the regression point of view, and particularly a logistic regression. So I always start with thinking about the logistic function, which is a function that looks like this. And you could graph it with these parameters. It has two parameters, which we sometimes call a bias and a weight. And the function would look like this with this particular set of parameters. So it has a nice, it's a nice, sometimes it's a sigmoidal, or it's called an S-shaped, or it's a squashing function that keeps everything between 0 and 1. The output is always between 0 and 1. And we can take this function and just draw it graphically, think about it graphically. Here in this picture, my input is going to be, an arrow coming from some variable. The bias term, we usually don't draw the bias term, but there's usually a bias term that's also just that b parameter. And the weight is a property of the edge in this particular arrow. And the weight means we're going to take the weight and multiply it by this x value. And then we have some output. And we sometimes, when we draw a node, we always try to remember that there's some activation function. So there's some input, and there's some output, and there's some activation in the middle. And sometimes we call it a unit, sometimes we call it a node. And sometimes we think about it as transforming input to output. And of course, the goal is that given some data and some outputs, we're going to find parameter values so that the output equals 1 when the target equals 1. Okay. So let's think about this again. So here I just wrote the equation. We have a graph. And if you think about the way parameters can affect this, in general, the b parameter, the bias, kind of shifts the curve. And the weight parameter can change the slope. So just by changing b and w, we can get a lot of different variations on what this function looks like. So this is just some, a few variations. And then we can go further and say, well, let's take this example. Imagine I have one input. I have two logistic units. And I'm going to have these two functions at those two units. So the parameters for the one unit and the parameters for the other unit produces these two functions. And if I ask you, what would happen if I add those two functions together into some final output? What would the final output function look like? Well, just visually in your head, look at the graphs, try to add them together, see what that would look like in your head, see if you can make a picture, and tell me if you come up with this picture. So my function of x1, my output function, is a bump function, or it looks like an inverse or a cosine function at some point, in some ways. And if you take this and continue this kind of procedure, you can create very complicated functions of your input. So here I'm not going to go through this. I just drew some pseudocode and what the functions look like. And as you continually add outputs and into new combinations, you can get really complicated looking functions. And the general point is that as you add layers, multiple layered networks can represent any logical or real valued functions. And in that sense, in the machine learning kind of terminology, we would say these are unbiased models because they can learn any function. But when you have unbiased models and you're adding parameters, you have a lot of potential to overfit. So that's really the name of the game with these kinds of, with a lot of different models, but especially with neural networks, is you really are doing what you can to avoid overfitting. And you're trying to create the model, you're trying to create connections and layers that can represent the kind of problem you're trying to solve. Okay. So we can add layers and nodes to our individual graph. Instead of, we're not drawing one unit anymore. Now we're drawing a bunch of units. And every unit, of course, we said has weights and bias terms. There's input and output. And we can label these things as an input layer, a hidden layer, and an output layer. And we have to keep in mind that our input layer is really an input vector. We're inputting one vector at a time. And our output is going to be possibly an output vector, possibly just one target. Again, these arrows, when I draw it, it represents weight parameters. And so we can start also thinking about what the algorithm looks like. First, you're choosing parameters, you're choosing a configuration of the network, you're choosing the number of layers. Maybe you're choosing a connectivity pattern. Maybe it's just all connections. Sometimes you don't have all connections. You have an architecture that is geared towards your problem. And that's what we'll see with convolution networks. And you're choosing activation. So they're not just logistic function activations, but there's other kinds of activations. And the first thing you would do when you have some input is forward propagate it. So you apply the input to your first layer. Sometimes I draw it out as a layer 1. Sometimes people don't draw it out. So we apply our input data, we calculate node activations at the next layer, and we keep propagating that forward. And then for error correction or for training, we do the back propagation step. And in this scenario, we're taking our outputs, we know what the target is supposed to be, and we take some kind of derivative or some kind of error correcting procedure, and it's usually a derivative in neural networks. And we're going to pass that information about errors and derivatives at the uppermost layer, layer 4, we're going to pass that information backward. And the way that works is through a chain rule. So if you remember from your days of calculus, with composite functions, you can use a chain rule and get your derivative for all your parameters. The problem is, the issue is that this takes a fair amount of computation because you're back propagating information that came from, maybe it came from all the hidden units. And so now that information has to come back to all the hidden units. So it really becomes a little bit, in the programming, where if you were ever to program this, it becomes a little bit of a indexing nightmare. But and the information, the information from one particular hidden unit is spread out to all the units in the next layer, and each unit gets spread out to all the units in the next layer. So there's really a lot of dependencies. And one thing that people were finding when they first started doing neural networks is that as you have more layers, the information about the error and what impact each weight has on the error, that information is diluted. And so this is called the vanishing gradient problem. As you go backwards to lower layers in the network, that information becomes less strong. You can have problems knowing how to update those weight values. And finally, in your algorithm, you're going to have some kind of update term. So I'm not going to say much about this, but this is a typical kind of thing you would do when you're using stochastic gradient descent in a lot of machine learning models. And just let me formalize or restate the algorithm in steps. Your first step, you're going to initialize weights. You've chosen some architecture, you initialize some weights. You're going to have some loop where until some stopping criteria, we'll talk about that, you're going to have a forward propagation step, a backward propagation step, update your parameter step, and then you stop on your criteria. And typically, your criteria is going to be something like when the validation loss reaches a minimum or convergence. So you're going to have a training set and a validation set, and you're looking to see when you're using the training set just to calculate the weight updates, and you're testing on the validation set to see how it's performing. So that's sometimes called our criteria in a sense is early stopping, or we're avoiding overfitting. Now it turns out with all these steps, there's really a lot of some of it. Sometimes heuristics. There's a lot of options. There's ways to make things learn faster or better, and this a lot of when we start developing neural networks. This is a lot of options. A lot of the bells and whistles that you're going to be looking at have to do with parameters for these steps. Okay, I'm not going to go through these examples, but we'll see this when we start doing our tutorials. So as I said, there's this issue with the vanishing gradient problem, and as you have more layers, you're going to have more diluted information in your lower layers. But one way to mitigate this is to use a different activation function. So people discovered that this ReLU, or rectified linear unit, is a good way to help propagate errors backwards. And on the bad side, it's unscaled. But on the good side, the derivative is constant. So this is why it helps propagate back to that derivative information. And as you can see from the function, there's a cutoff where if it's less than the cutoff, it's 0, and greater than the cutoff, it's just a linear unit. And it turns out this, as I said, helps mitigate the vanishing gradient problem. So this turned out to be a real good thing for deep neural learning. So in summary, neural networks are flexible and powerful learners. The hidden layers are really learning some nonlinear transformation of the input. As you combine activation functions and layers, as you combine layers and nodes, you can get interesting transformations of the input. And there's a lot of heuristics about what works. So there's, these aren't, they're based on principles about what a network is doing, but you'll find that with all the possible options, different kinds of activation functions, people kind of will say, okay, these work well, these don't work well. And so you kind of need to look at, and we'll see this again, when we're implementing a neural network, you to some extent, you're going to look at the kinds of options and see what are the default parameters. So for example, in something like Keras, they implement a lot of these heuristics in their default parameters. On the bad side, neural networks are hard to interpret. Sometimes people talk about them as black boxes. That's probably a little bit extreme. They're not completely black boxes at all. But they are, they take some effort to interpret it compared to, other kinds of machine learning models. You need more data as you have more parameters. If you add more layers, you're going to want to have more data or ways to avoid overfitting, because the data helps you avoid overfitting. And of course, there's lots of parameters. So computationally, these can be expensive. So we can say quickly, what is deep learning? On one hand, based on what we think a network, based on what a network is doing, and based on what we've talked about, the way layers and units can combine to create transformations, we can say deep learning refers to learning complex and varied transformations of the input. Okay. It sometimes is talked about in terms of discovering useful features of the input. And really more practically, it's a neural network with many layers. That's how people talk about it most of the time. All right, any questions so far? If you do, someone let me know. All right, so that was just a general introduction to neural networks, but let's talk about convolution neural networks. Convolution neural networks are specifically for vision and image processing problems. So imagine I have this. This is a database of handwritten printed digits. It's called MNIST. It's been around for a while. You might have heard of it. It's kind of the hello world of convolution networks. So we'll go through this. The database is black and white images of digits taken from, I can't remember if it's taken from postal code handwriting letters or handwriting envelopes, handwritten envelopes. And as you can see, there's, some of these digits are pretty, they're pretty consistent. Some of them have quite a bit of variations. If you look at these eights, here's an 8 in the 7th row, ninth column. It doesn't even look like an 8 to me. It could be a 9. I don't even know what that is. So there's a lot of variation the way some of these digits come out, and so it's kind of an interesting test. And our question is, how do we classify digits? So let me zoom in on one of these digits. Here's a 7, and what I've done is I've taken the grayscale image and I've just scaled it a little bit to go between values of 0 or 10 so that we can look at these numbers and not have to deal with fractions. And let's say I zoom in on one part of the image. So here I've zoomed in on the upper left corner of the 7. And in this part of the image, you can see that, some of the values are 10, and right along the edge, they're a little bit high, a little bit low, and then there's zeros. So this is so let's do this. Let's take a 3x3 patch of pixels and apply a filter to it. This is the standard computer vision technique. So I've created a filter here with -1 on the left column, 0 in the middle, +1 in the right column. It's a 3x3 patch. I'm sorry, a 3x3 filter. I'm going to apply it element-wise to a 3x3 patch of the input. So for this particular patch, it's all zeros except the 3. So each element-wise multiplication is going to be a 0, except for the last, the bottom right is going to be 3 times +1. So when I work out that multiplication and then I add all the values, okay, I'm going to put the answer into a new map. So that's the result of the first convolution. I'm going to take this filter and I'm going to slide it over 1 pixel. So let me go to the next slide. Okay. All right. So this is the result of image patch times my filter. I'm going to slide my filter and I'm going to perform the same calculation, the convolution calculation, and I'm going to write the answer into the next output cell. And I'm going to repeat this process again. I slide my filter, and now I have, all zeros on the first 2 rows, 3, 7, 6 on the last row, which produces a -3, 0, and a +6, and my final output is a 3. So the sliding the filter is a convolution operation. I'm multiplying each patch by this filter and just taking a summation, and I'm producing a new output map. And notice the output map is going to be a little bit smaller than the input map. If I keep doing this operation, I end up with, let's see, my input map was 5x6, and my output map is 3x4. And this is because you're sliding the filter, and when you get to the edge, you stop. So let me ask you this. What does the highest values in the feature map represent? All right, let's think about this. So we're looking at a corner of the 7. I've done this convolution operation. My highest values are right here in this feature map, 21 and 17, and next to that is also a 15. So the highest values are right in this lower left part. And let's do one more step, just to make this a little bit more maybe interpretable or maybe optimal or efficient. We take another filter, and this time we're going to take the maximum over a certain number of elements. So this is called a max pooling. So we're going to use a 2x2 filter and just pull out the maximum value. In this case, in the upper left corner of my output map, my maximum is 17. I'm going to take this 2x2 patch and replace it with one value, 17. And I'm going to repeat that. So it's the same. It's almost like the convolution operation. I'm just doing a maximum operation though. I don't have any weight, any what I call a W or filter. So I'm going to slide the max pooling operation and produce this final output map, which is now 2 by 3. So the max pooling is a way to kind of summarize your output map and downsize it. All right, so I've now taken my original 5 by 6 patch, transformed it into a 2 by 3 feature map of edge gradients. And that's really what we're looking at. That's really the function that we're kind of representing, is that this particular filter is appropriate for detecting, the gradient of an edge. All right, so I went through that a little bit, hopefully slow, but hopefully you kind of get the intuition about what it is that people think about when we're doing computer vision, for example. But there's really many kinds of ways to think about filters and many kinds of possible detectors. And how would you come up with, if you look at all the digits, how would you come up with all the kind of features that you want to pull out that are relevant to predicting the class of the digit? So building features is hard. So instead of trying to build the features by hand, if you have enough data, you can just use weight parameters. And in this case, we're going to ask a neural network to find values for those weights. So a convolutional network, the filter values are the weight parameters, and those are going to be learned. And that's what we mean by feature discovery. A convolution layer is a set of feature maps where each input map is, where each output map is derived from the convolution of one filter with the input. Okay, so we're going to see what that looks like in a second. But even where we are so far, we've already said, we've already added certain kind of complexity. So we've added certain hyperparameters. We have to choose the size of the filter, and people have discovered heuristically that it's probably better to use smaller filters. With smaller filters, you're going to capture the fine granularity of your image. Not only that, with smaller filters, a small filter followed by another layer of small filters is the same as one filter of a bigger size. So heuristically and principally, it seems to be better to use smaller filters. Maybe it's a little bit more computationally expensive, but it seems to work better. How many pixels are you going to slide over? People typically choose 1 or 2. How many filters are you going to have? And that, to me, I think depends more on the problem. The number of filters you have is almost like the number of features you think are important. So we'll talk more about that as well. Are you going to do max pooling or not? So max pooling was nice because it kind of summarizes the image. It helps downsample an image. Some people, think it's really something that helps performance that way. And so usually people use some pooling layers, but not always right after every convolution layer. Sometimes you have a block of convolution layers, and then you might do a max pooling. So you'll see some variation in how that gets implemented. And let's put this all together and see what a convolution neural network looks like. So here I have an image, and we're going to, when you run an image kind of processing or image classification problem, all your images should be the same size, typically, and you're going to crop it or resize it in some manner so it produces, in this case, a 224 by 224 by 3 input image. And remember, the 3 is because we have red, green, blue channels. So that's our input. Our convolution layer is going to look something like this. We're going to create a filter. In this case, this example is from the AlexNet, which was the original one that really made it more of a splash and had a big impact on the field. And this is using a 5 by 5 by 3 filter. And the 5 by 5 is what the person chose as your filter size in height and width. The 3 has to be there because you have 3 channels. So 5 by 5 by 3 is what, 25 times 3 is 75. So that's 75 weight parameters. But remember, this is applied to the entire input. So it's not, it's one filter that gets slid over this whole image. And so the feature map size depends on the filter size and the slide parameters. So the output size depends on some of these parameters. And we're going to do this for many filters. So remember, one of the hyperparameters was to choose a number of filters. Each filter is going to be a 5 by 5 by 3 filter, and each filter is going to give you one feature map on the output side. And those maps get stacked up. So your output is going to be whatever size the output feature map is multiplied by the number of filters. And this is what we call a convolution layer. Again, the thickness is the number of different maps. Sometimes it's called channels, sometimes it's called filters. Nowadays, I think people typically just say filters. We might add a layer of max pool to downsample this feature map, or we might just add another convolution layer. Here's what the network looks like in its full diagram. So this is the AlexNet. Let's see, it had 96 features in the first convolution layer, followed by max pooling, and then I think that's 256, followed by max pooling, and then 3 blocks of convolution layers. And at the end, your feature maps are getting smaller and smaller, right? As you're taking a convolution filter and sliding it over, your output feature map for each filter, it's getting a little bit smaller. And at the end, though, you're going to do a classification task. So that means you're going to take your final convolution layer, you're going to flatten it and present it to essentially a multi-layer perceptron. And in this example, this was applied to an image recognition problem with 1,000 objects. And nowadays, as people have developed this more and more, we're seeing large convolution networks that are turning out to be feasible with GPUs. Some of them are more than 100 layers. It needs more data. It needs lots of data. There's lots of heuristics to avoid overfitting and increase efficiency. And these things are turning out to have really good performance. So what do learned convolutions look like? So in this particular problem, particular example of the AlexNet, they published some of the convolution filters. So the filters themselves seem to show things that look like kind of edge detectors. So if you look at the black lines, those are low values followed by high values. And remember, these are the weights. So remember that particular edge detector I showed you. The middle was 0, and then you had -1 and +1 on the left and right columns. So this is something not too dissimilar. They're combinations of, these weight values are combinations of low and high values, and they're going to, in some sense, they're like matching little parts of the input. But what's unusual is that some of these filters are, kinds of things you probably wouldn't come up with on your own. So some of these are very blurred and they're kind of white. Some of these are at funny angles. Some of these look like two edge detectors right next to each other. All kinds of angles. And then some of these are based on color, it seems like gradients of color or edges of color. It's not obvious to me what you would, how you would, if you had to interpret these filters, what you would say about them. But the nice thing about deep learning is that you don't necessarily have to do this kind of analysis. You don't have to say, oh, this is exactly this feature. It's the combination of all these features that make these things work. All right. And then we can also look at what the activations look like. So now we're looking at the output feature maps from the first convolution layer. After applying the rectified linear unit, and then the second convolution layer, and then applying the rectified linear unit, and so forth and so forth. And here's the output after pooling. And remember, as we go from lower layers to higher layers, the feature maps are getting smaller. So if you look at the far left, I'm sorry, I had it backwards, the far right, These convolutions are smaller feature maps. The pixels are larger, and they should be representing, hopefully, some more abstract features or combinations of lower level features. They should be representing something more abstract that's related to the object that's going to be predicted. So that's one way that's probably a good way to think about how these feature maps are working. The lower layers that are close to the image are really just doing simple transformations. Maybe they're highlighting edges as you go up. The higher layers should be highlighting combinations of lower features. So maybe it's a combination of edges and color, who knows, it's hard to say. But they're smaller feature maps, and they represent, sometimes people call these things equivariant, because at the higher levels, these combinations of features that are represented that will help you predict a car or a truck, those features are not necessarily tied to a specific point in space. So it's equivariant in the sense that different parts of the image can all activate some car feature. All right, so let me summarize this. Convolution networks work because convolution layers have special architecture and a function. They're biased to do certain kinds of transformations. These are the transformations that are specifically looking at, little patches and looking maybe for some kinds of little features. The lower layers have less filters, and this, again, this is a heuristic thing. You'll see that your lower layers will have less filters, represent simple local features for all classes. Your higher layers, you tend to have more filters, and that's going to cover, each filter is going to cover sort of a larger region of the input space and represent object class features. Okay, so any questions there? I'm going to start talking a little bit about the Keras commands, and then we'll go into an exercise. So our exercise is going to be, again, it's going to be convolution network. Example on the digit classification. As I said before, this is called MNIST. We're going to be using Keras. And when we do this, I'm going to show you, talk about the code in a second. But our basic workflow, and this is similar for lots of machine learning models, we're going to load prepared data. So we're going to have some, typical Python statements for setting up matrices and reading files. We'll define a model. Okay, so the Keras, remember, Keras is integrated in TensorFlow. It's a kind of a higher level language to help us set up neural networks. And I'll go through some with this example. We're going to define a model, we fit a model, and then we test the model. So these are the same kinds of steps you would do with lots of machine learning models. The coding wise, what's probably most different is defining the model. So let's zoom in on some of these model statements. Here, this is a Keras models sequential. There's two kinds of model building. One is sequential and one is using a functional. We're going to talk about the functional more later. But the sequential is basically saying, I'm going to set up a model where each layer feeds into the next layer. So it's not as complicated an architecture as we could do. So we're using a sequence of layers. And in this example, I'm going to take my input image. I'm going to use a flatten just to turn it into a vector. So I'm taking my 28 by 28, I'm just turning it into a vector. And then I'm going to add a dense layer, which is really just a hidden layer that's fully connected to the input. So this is the simplest version of a model that you could use, perhaps. This is basically a multi-layer perceptron. Not even a multi-layer perceptron, it looks like a one-layer perceptron. Okay, so I define a model with the sequential statement. I have the model object, and if I wanted to add a convolution, I could just say, oh, okay, take my model object and add a convolution layer. So there's an add function. You tell it what kind of layer it is. You give it the layer parameters, and it adds a convolution layer. Okay, so in this example, I said there's 16 filters. the kernel size, which is the filter size. So I was calling it filter size. Here they call it a kernel size. You tell it the number of strides, the activation function, and that's your convolution layer. Notice that when you give it the input shape, you don't tell it up front how many inputs you have. So the number of inputs you have is something that's going to be given when you're fitting the function. You're going to tell it use this number of inputs in a batch. So we'll see that example. All right, so let's go start an exercise. Here I'm showing you, okay, so you can go in through the portal or go into, there's two ways to get in and expand. So let me go switch screens to the portal. Let's see. So I do have a Jupyter notebook open. I'm going to close this one. I'm going to see if I can get in through the portal. I was having trouble earlier today getting in through the portal. So there's two ways. I'm going to first try the portal. I'm going to open up a Jupyter notebook portal. And you guys should all go ahead and start doing this on your own. You can either go in through a portal, or if you log in directly to Expanse, you can run the Jupyter, I think it's called Jupyter Computer TensorFlow is the alias to bring up a Jupyter Notebook session. Okay, if you run Jupyter Computer TensorFlow, you'll get a URL associated with it. So you can either do that or run through the portal. I did this a little while ago, so I have a Jupyter session running right there. But I'm also going to try doing it through the portal. And if you run through the portal, let's see. We should be able to use, I'm going to do 60 minutes. We should be able to use the reservation. 128 cores. Let's say 240, I'm going to say 244 gigabytes.
Well, you'll need to put 243 or less.
Is there a question?
Yeah, Paul, sorry, there's you need to put 243 or less or it won't start. Sorry, for your memory request.
All right, 242. Because why would we put a 240? Isn't 243 a prime number? I don't think we should use prime numbers. That's just my personal opinion. All right, so our reservation is SI22 day 4. Our directory, home directories, I'm working directories, our home directory, and this is, I'm going to use the Jupyter notebook. All right, so just let me review that. So CRL 155, compute 60. I think we need this for.
I would also recommend putting the QoS normal-EOT.
Normal-EOT, small letters?
Yes.
Okay. All right, so I'll leave that up on the screen a second. So if we submit this, this should start our Jupyter notebook. So everybody go ahead and start up a Jupyter notebook either way, either through logging into Expanse directly or through the portal. I'll give you guys a second. Okay. Okay, so I've started my portal session. And since I had already started a session earlier, if I do a SQ command for my training account, ooh, look what I have. I have one that's pending. I have a couple other ones that are running that I didn't know I had running. Let's see. So I'm just going to leave them alone because I'm not sure which one is which. Pretend you didn't see that, Marty. All right, so my session is starting. I already have a session up and running, as I said before. Hopefully you have updated your GitHub repository, and I don't think I updated it last night. So as long as you did it yesterday, you should find the latest and proper slides and notebooks. I'm going to go into the I think we are, yeah, here it is. So 5.1b has the Intro to Deep Learning. The Intro to Deep Learning folder has a PDF, and it has 4 notebooks. We're going to first do the intro, and I have an intro without a solution, intro with a solution, and then later we'll do the hypertuner one. So open up the intro without solution, and we'll do this as an exercise. Is everyone there? Does anyone need more time, or should I wait? How about some thumbs up if you guys are doing okay? All right. I got a couple. I'll give you guys a couple minutes because I know when I started these sessions, it takes it takes a minute or two for the session to get going, especially because we're all doing it at the same time. Is anyone having problems? If you're having problems, something's not happening right, let us know, and then we can try to address it. Okay, so what I want to do is introduce, I'm just going to go through this notebook. I'm just going to review it first and introduce the idea and the step and the segments, and I will let you guys work through the exercise. So I have a couple spots where there's blanks, and I have some hints of how to fill it in and what to try. So we'll review the code. We're going to look for the model sequential statement and fill in blanks in there. That's, like I said before, I think that's the other than, for your typical workflow, that's where you're going to really be coding something that maybe you haven't, kinds of statements you haven't seen before. We'll run the notebook, we'll look at the outputs, and then we'll play around with the filter size and a couple parameters. And as you go through this, think about, gee, I'm classifying 10 digits. What do I need? What kind of architecture do you need? How complicated should this be? Should I do more layers? Should I make, more or less filters? I mean, it's so easy when we're building neural networks to just throw more resources at the problem. But that's not always the best thing to do. All right, so I have in this code, there's import statements at the beginning. You can look at those, they're pretty standard. I have some, the next cell is loading the data. Those are also pretty standard. There's not much more to say about that. Look at those at more detail at some point, but you should be able to just run those. And for the first item I have is to fill in some blanks for the convolution parameters. So I have a link to the Keras API documentation, and I have some suggestions of what you can try for filters and filter parameters. So you want to look at the documentation, see how that's coded, and then you can see in this cell where the blanks are. And the reason I wanted to set up the exercise this way is when you're developing or when you're implementing neural networks, you sort of have an idea. You typically have an idea what you want to do, what you think might work. And then, for a tool like Keras, I am finding myself just constantly going to the documentation and say, oh, okay, I wanted to try some different parameter. Exactly how is that parameter specified? What are the options for that parameter? And so you want to get comfortable looking at, seeing the documentation. I also have a second step to think about the optimizer. So in your model definition, I'm going to scroll down a little bit, scroll down. There is a compile step. The compile step is really just kind of, it's not a compile per se. I tend to think of it as just like assembling together the parts. I think technically it's doing something more like helping create a the computation, helping set up the computations for when you actually do the fit. There is an optimizer option and a loss option. So here I've set up the loss option as categorical cross entropy. And there are, your loss options are going to come from the task you're doing. There's a bunch of loss options in Keras. They're kind of standard for what you're doing. If you're doing classification and you have outputs that, in our case, we have 10 outputs and only one output is active at a time. So that's going to be a categorical cross entropy. If if it's binary, you have a binary cross entropy. If it's regression model, you have maybe mean squared error. So your loss functions are typically are kind of standard, but there's some variations there too. Your optimizers are, we're going to talk a little bit more about that later, but your optimizers are a little bit up to you. So here I've suggested stochastic gradient descent. In Keras, you could just write SGD as abbreviation for that. But I want you to change it to the atom optimizer. So for that, I've asked you to go look into the documentation to see how you would specify that. Okay. And then you can change the number of filters. Okay. Oh, I've asked you to fill in some of the parameters for the fit function. So this should be hopefully you should be able to see quickly from these examples in Keras website how that fills in, and the callback function. And then the rest of the notebook is just plotting images. So take your time. I'm going to give you guys, let's say 10, 15 minutes, let's say 10 or 15 minutes, and I'll check back in and see how we're doing. But take your time, go through, and let's see if we can run this notebook. And if you have questions, I'm just going to sit here and do this really slowly. In a few minutes, I'll let everyone get started. But if you have any questions, you can either, put it on the Slack channel or just let me know.
Oh, there's a question in the chat.
In the chat, okay.
Yeah. A question is it common for there to be more testing data than training data? Can you explain how you decide how much of each to use?
So there is a lot of discussion about how you're supposed to set up your training and your test data. And remember, the whole reason we have test data, this could be, we could do a long discussion. The whole reason we have test data is to get an estimate of how our network is going to generalize. So remember, that's the name of our game, is that we're trying to build a model that can generalize. And that's our main, unlike statistical inferencing, we're trying to come out with some significant p-values. Here, we're trying to come up with some good performance. So that's the main thing we're looking for. Now, if I give you a bunch of data, and I don't know how much it is, let's say I give you whatever amount of data, and you used to said, okay, I'm going to build a network that's going to perform well for data I haven't seen yet. And if I give you, so I give you some data, but the rest of the data you haven't seen, I don't have it. Let's say tomorrow, it's going to come next year or something. So you have the data and you have to decide, well, I need to split my data up in a way so that I can figure out how it's going to generalize. If I give you some data, then typically what you say is, or a very accepted way to do it is to take your data, split it up into 10 parts and do 10-fold cross-validation. And so you train your data on 9 parts, and the part you left out, you're going to test it on. And if you do that for 10 different arrangements of your data, for 10 different combinations of splitting your data, of splits of training and test data, then you kind of come up with an estimate of how good your model will perform. So in those cases, you're taking your training data and really you're splitting it up into a training set and a validation set. And hopefully someone can, and then when you actually judge the performance, you're going to hopefully have another test set. So what you're going to typically do is for whatever data set you have is you're going to have training and validation, and you're going to use that to come up with an estimate of how it's going to perform on data you haven't seen. When it comes to a lot of, so that's a typical machine learning model kind of thing. When it comes to deep networks, let me go scroll down to this fit function. Oops, I went too far. When we look at this fit function, you know, Keras has this. Let me go. You know what? I'm going to go into the documentation. Let's see if I can find this. Hang on a second. Okay. So when we look at the fit function, we're supposed to give it some training data, and then we have this. We can either give it a validation split. We can tell Keras, you know what? I have some training data. Split the data up for me into a validation set randomly. Or we can tell it, here's the validation data. So when you do, in your typical machine learning model, you're going to do a 10-fold cross validation, and you're going to say this, you know, this is a training, this is validation. Case number 1, you're going to do this for 10-fold. So you're going to have another case number 2. This is my training data, this is my validation data. And you split up your data so that there's, you know, each data point gets to be a validation set, or in the training set. So that's your typical 10-fold cross-validation. A lot of what people do with deep learning is they say, well, you know, I have so much data that it's not really going to be efficient for me to do a 10-fold cross-validation. So what I'm going to do is a split. And I'm going to say split it by some percent. And there's kind of a heuristic about what should be a good percentage of data that you take out and you use it only for test. If you have a lot of data, then you're probably pretty good at, you know, if you have a lot of data and the statistics are well sampled, then you're probably pretty good at just saying, no, just take out, you know, a third of my data. If you don't have that much data, then that's when you have to make a harder choice. If I don't have that much data, I said I need to use as much data for training as I can. But I need a lot of data for testing. So, you know, how do you split it? And that's when it becomes a lot harder. That's when it becomes more important to try to do cross-validation, which you'll find in a lot of the deep learning examples. People just say they'll take a split percentage, and you know, maybe it's a third, maybe it's a fourth, and they'll say, well, I have so much data, I don't need to do cross-validation. I'm still going to get a good estimate of my generalization error. I'm still going to be able to find a good set of parameters by, you know, using this split. When you have less data, you have to be more careful and use, you know, probably cross-validation. When you have more data, you can just be a little bit more cavalier. I don't want to say cavalier, but a little bit more flexible in just how you split the data. And remember, when we're setting up parameters, like we got number of filters, number of layers, all these parameters we're looking at, you want to, for each, you know, how do you choose parameters? You want to get a good estimate of your error. And that's the name of the game. That's the whole point where, you know, why we do this validation of things. So that's hopefully that's a good answer or a helpful answer. I don't know if it, I don't know if it's more confusing or not, but it can be, you know, depending on your situation, it really can be something you have to think about carefully. If you have enough data, then it's a lot easier to deal with. What is enough data? That's a harder question. And you know, for some of these image classifications, you know, you need, for some of these large problems with these large networks, you need, you know, hundreds of thousands maybe. And Maya's going to talk about this more, but there's an image conference where they do this competition, and I think they were using 1,000. You know, they typically use 1,000 image categories, and I don't remember how many images, 1 million images or something like that. Okay, so let's go through this. Let's go through this solution real quick. I'm just going to run through the steps. So my import, my load data, this runs fairly quickly because it's not a huge, these are not huge images. And again, I'm running this on a CPU, not a GPU, because I don't need a GPU. They're small enough images. I'm not using too many layers. So I set up a build model. I set up a build model function, and I intended for you to use the number of filters parameter as the first parameter in the convolution layer. So that's a variable called number of filters. 3x3 filter size, the ReLU activation. I've just set it up with the SGG optimizer for this step, and I'm just going to run the model. So the summary, I build a model with the number of filters. Here I chose 16, and then I do a model summary statement. This is a nice feature of Keras. It'll summarize your model, and when you start developing models, you're really going to, and we'll see this in our later exercise, you really need to, at some times, not all the time, but every so often, you really need to look at the output shapes and really understand, well, what is the output shape that's coming out of your model? Where are all the parameters? So here in this example, I have 76,000 parameters. 73,000 of those are coming from the dense layers for classification. So, convolution by itself doesn't necessarily add a lot of parameters, relatively speaking. It's really when we flatten it and try to do the classification that all of a sudden we get a lot more parameters. And that's because here I've done a max pooling. I've got a 12 by 12 image size, which is pretty small. I started with 26 by 26. I'm down to 12 by 12 with 16 filters. But when I flatten that, that turns out to be 2,300, a vector of 2,300 length. And depending on how many units I have in my dense layer, that's going to give me a lot of, remember, this is a dense, fully connected layer. That's what it means by dense. So I have 70, that's how I get so many parameters. Okay. And then I ran the model. I'm not going to run the model again, but when I ran it the first time, it used, I asked for 50 epochs. It used all 50 epochs. And the loss function, if you look at the loss function was still decreasing. So I could have run this more. I didn't reach the point where I had early stopping. But what I'm going to do, I'm going to show you something in a second. That's part of the reason. Well, let me just leave it at that. So it ran for 50 epochs. The loss function was still decreasing. If I look at, I can plot the loss function. Or sorry, here I'm plotting accuracy. So the accuracy is still going up a little bit. There's a gap between training and my test data set, but they're both still going up. I can plot an image. I can plot the filters. If you look at these filters, remember these are 3x3 filters, and there's hard to say what they're doing. If you look at the activations, so I have an input of a 5. This is the activation that comes out of the first convolution layer. It looks like the transformation that it's doing almost looks like, well, it's not really doing that much. Some of these filters don't seem to be doing much. Some of these filters are here, this bottom, this on the last row, the left column. A transformation of the original input is almost like an inverse, but there is some, some higher values along certain edge. So this almost looks like an edge detector for the bottom part of a 5. That's very, it's very tempting to kind of interpret it that way. This rightmost bottom row last column looks like it's detecting the edge of the bottom of the 5 and the top of the 5. So that one's kind of, look, if you had to interpret that filter, you would say, oh, maybe it's a diagonal line. Let's see. So that filter right here, the bottom row, last column, that's a 3x3 filter. And you can see it's got low, it kind of looks like it's maybe doing processing for diagonal lines. Okay, so that filter is like matching diagonal lines. It's hard to interpret all the filters, but it's tempting. Okay, so hopefully you see that. If you've, what I want to show you is let's change the optimizer. Okay, so if you went into the optimizer section of the documentation, it says, oh, here I could just stick in this function as my option for the optimizer. So right here, okay, so my optimizer is going to equal to this function. I can run this and just run the whole thing again. And let's see, so I've changed the optimizer, and look, the atom optimizer is just a lot faster, a lot quicker than the stochastic gradient descent. And we're going to talk a little bit more about optimizers in the next part. All right, so let me plot this stuff. Okay, so it's a little bit more accurate. It did reach an early stopping point, and the solution, it's kind of the same. All right, let's try one thing I wanted to play around with. Go and change the filter size to 16 by 16. So this is my build model function. Again, I'm going to use 16 filters, but now I'm going to use really large filters. So let's do a kernel restart and run all. Oh, doesn't like something. One thing about Python, it's not great at giving you, gives you a lot of messages. But let's look at this error. One of the dimensions of the output is less than 0 due to downsampling. Oh, okay. Well, we know what we changed. And what it's telling us is that, remember I said the size of your kernel and the number of strides affects the size of your output map. These filters are too big because it downsampled so much that there was nothing to output. So I'm going to change it to, you know what? I'm going to change it like this. I'm going to keep that 16. I'm going to make this 3 by 3. Let's see if this one works. Okay, so it ran. So it's in the running. And again, my loss function goes down pretty quickly. It reaches an early stopping point where it's not decreasing anymore. Let's see. Okay. So it's pretty much flattened out at that point after 12, 13 epochs. So there's my 5. Now remember, my filters are 16 by 16. So when you look at filters that are this big, you can see, I think intuitively, they're picking up parts of the image, no longer just little edges, but maybe entire, quote unquote, features. Some of these filters look like they're picking up on what a 0 looks like. And some of these might be more about like some kind of part of a 7 or maybe even a 3, I'm not sure, or a 5. So remember, these are 16 by 16 filters. So for example, on the top row, second column in my particular example, it's, this is a filter that's going to be sliding over the whole 28 by 28. So this could be, for example, the corner of a 7. Maybe it's the middle part of a 5 or a part of a 3. Okay, I hope that kind of makes sense. I hope that gives you some intuition about what, this is the trade-off with larger filters versus smaller filters. Okay, and then the transformation that happens is going to be a lot more dramatic. All right, so that's something you can play around with. Again, you know, there was a question. I had asked this question. Well, what's the fewest number of filters? You know, you can go back and change this number of filters and see how performance changes. You again, you know, you have to make sure you give it enough epochs so that it reaches a minimum. So it does reach a point where it's early stopping. In this particular network, I'm going to scroll up a little bit to, so I was using the metric of accuracy as, it's going to use that for early stopping. Oh no, I'm sorry. In the early stopping function, you can tell it what metric to use for early stopping. Here it's using the validation loss. So if we scroll down, if you look at these epochs, the validation loss is plotted right here on my screen. It's right here, and the loss, the minimum was, looks like 0.4187, and then it started going up. So that's why it stopped after 13. Oh no, the minimum was here, 0.37. So it's epoch 8 reached the minimum. And if I go back to my, see, look at this. I said, use the validation loss, look for the minimum validation loss, run for 5 more epochs before you decide that you've actually reached the minimum. That's what the patience parameter means. So if you go back and play with this, you can play around with different values here. You can try different number filters and just get used to, you know, some of these parameters that are used for running these networks. Okay. So I'm going to stop there with this exercise. I'm going to leave my session running. We're going to go back to slides. So this will go for, so what I'm going to do now, let me scroll through. Okay. So I'm going to switch a little bit and talk more generally about hyperparameters, tuning, and workflows, and then we'll do a shorter exercise. So this session goes for another, I think I have probably at least a half hour. And then I think we'll have time for a break then. Does that make sense, everybody? All right. So let's say you have some project and you have an idea of kind of network you want to do, but as I said, there's a lot of options, a lot of parameters you have to think about, you know, and some of these are hyperparameters that we're going to need to do a little bit of exploration. And the way you go about coming up with your, you know, choosing a hyperparameter, coming up with what you think is like a reasonable choice of your best hyperparameters, it's really a combination of exploration and exploitation. You kind of explore the problem for different parameters, and when you find a region or a combination or a configuration, sometimes we think of these as a configuration of parameters. When you find a configuration that seems to do well, you want to focus more on that area, on those particular sets of parameters, and that's the exploitation part. The other thing to think about in general for a project is to think about, you know, what is a good job workflow on our batch systems. You know, Marty, I think, had a really good, a lot of detail about high throughput computing and data management. So you want to think about, I'll think a little bit more about that. Again, GPUs for large models, large data sets. At some point, you're going to, you know, want to switch to GPUs. It's nice to sort of develop on a CPU. It's possible to do that. And when you have bigger bigger workflows, bigger models, bigger data sets, you know, there are ways to run it so that you can have a checkpoint and you can reload a model and start retraining from a certain point. We do have TensorBoard. I do have an example of how to run that. And if you get to the point where you want to reuse TensorBoard for certain kinds of options, I find that I don't use TensorBoard a lot myself, but people do. And I think it does have some nice profiling options if you get to that point where things are, you think you have a bottleneck or something that's not quite running right. So it can be useful. So hyperparameters. Hyperparameters, I tend to think of hyperparameters in three different sets. You know, there's architecture parameters where you're choosing how this network is built. There's these algorithm hyperparameters. So we talked about the optimizer, for example, which optimizer you're going to use. And even the optimizer has certain parameters, learning rate. Stochastic gradient descent has a momentum optimizer, which can make it learn a lot faster. The number of epochs. So these are things that surround, like I said, the algorithm. And then there's other parameters that I tend to think of them more as just being good for performance in terms of the amount of time it takes to train. So the batch size is a parameter, and typically it depends on your memory. If you have a lot of memory, then large batch size is better. But the batch size isn't necessarily independent from finding good solutions. So, you know, the larger batch sizes might be better, but maybe take up more memory. We're going to say a little bit more about normalization and initializing parameters. Those can help with efficient learning, but not as, in principle, they're not geared towards finding better solutions per se, but if you have more efficient learning, it's going to be easier to find better solutions or better configurations of parameters. Some of these options depend on your task. So loss function, kind of depends on what your outputs look like. If you're doing image processing versus something else, then you're going to use a convolution network, for example. And really often you're going to want to look and see what other people have done and see what works, because that's probably always a good place to help you choose your parameters and your network. There are some people who've written, done some analysis and written some recommendations. So in the book, for example, from Jaron about Keras and TensorFlow, it's a few years old now. He will actually state, based on his experience and what people have done, he thinks here's activations that tend to work better. So the scaled, this is the ELU stands for exponential linear unit. It's just an exponential function with some parameters, and it has a certain form. So he suggests that exponential linear units would tend to be better than rectified linear units, would tend to be better than the sigmoidal kinds of things. Whether that's true all the time, it's again, these are heuristics, and no one can, I don't think anyone can say unequivocally that it's always this way. He talks about optimizers, and he actually has a decent introduction to these different optimizers and how they differ and how they kind of grew out of each other. So the stochastic gradient descent is slow, but if you give it enough time, it can be pretty good. But time is important too. The atom optimizer. So there's several optimizers that are related to each other, and off the top of my head, I can't tell you what the differences are. But if you wanted to go into that more detail. Hyperparameter search. So how do we do the hyperparameter search? It can take a long time. It's hard to find a global. Don't think you're going to find a global optimum. That's probably not the right perspective. It's probably better to think you're going to find a good solution and do a reasonable search. I think it's good to start with small data sets to get a range, get a good idea of like what are the good parameter values. An easy but time-consuming way is to just do a grid search. Once you have an idea of the range of good parameters, you just do a grid search over uniformly spaced values. So like 2 layers, 3 layers, 4 layers, 32 units, 64 units, 96 units in each layer. That kind of thing. You can just do a grid search over your possible configurations. And again, exploration and exploitation, which is like, a wide search and then a deep search. And there are some Keras tuner functions that can help you do the search. So that's what I'm going to do in the next exercise. There's a hypertuner function, a hypertuner, a hyperparameter search tool, and it's called hypertuner in Keras. It's a class that implements several search strategies. So one is called Hyperband. Hyperband is nice. It's kind of like setting up a tournament. Like you can imagine it just like it's not a round robin. Well, it's a little bit like a round robin tournament, and then a lose and you're out tournament. So it's the idea that you're going to do incremental training and you're going to weed out the worst performing parameter configurations, I should say. So that's what Hyperband is doing. There's something called random search, which is not the same as a grid search. It's a little bit more random. So instead of just evenly spaced values, it'll search through the space configurations with different range of values or different step sizes. Some people say it works better. It's not necessarily going to speed up your search, but it can be a better way to search your space because you're going to, the randomness, like uniform values doesn't necessarily capture, let's say, how the number of units can impact your performance. So the random search gets to that. There's something called Bayesian optimization. This is kind of from the field of function approximation. So it's almost like you do a little bit like a random search, but then you're going to use this method of trying to identify where you should go next, not just randomly. So it's going to look at where you haven't searched before and decide like, well, is that worth searching or not? So I haven't used that one a lot, but in the exercise, I'm going to talk about the Hyperband. So here's what Hyperband does. Again, it's like running a tournament. Each round of the tournament, it's going to look at several network configurations for just a small number of epochs. So round one in this graph, I'm showing you on the x-axis is the number of epochs, really the number of total epochs. They tend to call it resources because you can think of it as your time and computation resource. The first round, you run a bunch of configurations for, here in this, it's like 3 or I guess it's like 4 epochs. Then you pick out the best ones and you do a second round and you run each of those for maybe more epochs. And then you do another round with more epochs but less configurations. And then at the end you get a winner and you run that one for even more configurations. I find that using Hyperband is nice because it helps you do the exploration part and it doesn't take us that long. And then once you come up with a Hyperband, some better values from the Hyperband search, then maybe you could do a small grid search right around those Hyperband values. All right, so in the exercise, in the exercise, we're just gonna use this Hyperband tool, and it's nice because besides using the Hyperband tool, it's nice to go through this exercise to see how to build your functions so that they're more flexible and you can control the hyperparameters better. So what you're going to use, you remember the exercise before, I had a build model function. Here I'm going to have a build model function with the hyperparameter object. It's going to wrap around the build model function. So this is a way to kind of generalize your functions and make it easier to set up hyperparameter searches. With the Hyperband tool, there is a Hyperband function and it returns a tuner object, and that is basically wraps around the fit function. So I have something that wraps around my build function, something that wraps around my fit function, and that's how you're controlling this hyperparameter search. All right, so I'm not going to say too much more about this because in the next slide, because we're going to do an exercise of that in a second, but I just wanted to go ahead and finish up a couple thoughts. When you're organizing your workflow, ask yourself, what does it make sense to include in each job? Figure out how long your model runs take, and that's going to really kind of tell like how many model runs you should try in a job. Are you going to have one model configuration go through each validation data set, for example? What if your data set is huge? Maybe you don't want to do it this way. But this is your typical kind of way you would do it, I think. Oops. Sorry about that. So I recommend, organizing your jobs into reasonable chunks of work. And if you are setting up your hyperprinter search, and one other thing that's nice is to figure out a way so that when you are passing parameters, giving parameters to your model, you have a nice way to keep track of what those parameter values are as you start to run a lot of networks models and you're testing a lot of configurations. One way to do it is to use YAML files. It's just a kind of text file. So here I have a simple example of this. I think I have this example in the, no, I don't know if I have it in GitHub, but it's pretty straightforward to set up your job so that you could use a YAML file and pass parameters into your code. Let me go to the next slide. Okay, this is that example of that. You could have in your job set up parameters, give it to a YAML file, and then run your model through a Singularity container. And that way it's easier to have a YAML file that has a record of all your parameters. You could do this by passing arguments into a Python code as well. You could do this, some of this you could do, I think TensorBoard has, this could have this kind of information if you set it up right. Okay, so that's something to think about. I just want to throw that out there because when you start implementing these models, that's kind of a useful thing to kind of think about ahead of time. Python notebooks versus scripts. It's just a simple way to set up. It's nice to work with notebooks, but when you start running a lot of batch jobs, it's nice to just you want to run it in batch. A notebook isn't really set up to run in batch right away. You have to do some kind of transformation. There's a tool called Papermill that Peter Rose talks about. He has some lectures on it. I think he's going to talk about it tomorrow. A simple way is also to just use a notebook convert statement. And you just have to manipulate. You just have to change your notebook a couple ways, and then you could keep a notebook, and whenever you run it in batch, right before you run it, you do a convert, and it will run. As long as you set up these, turn off the displays. Okay, something else to think about. Finally, a note on using GPUs. We're not going into all the details about setting up GPUs for your TensorFlow code, but it's pretty straightforward. You can go directly. You can code the stuff that we're doing right now, and just run it on a GPU. TensorFlow will run it on a GPU device without really any changes. There's a couple things you want to do though. You want to take your code and split the data so it'll run on multiple devices. If you want to use multiple GPU nodes, that's a whole different thing, and I don't have an example of that. But using multiple devices will get you pretty far. Using even just one GPU device. Okay, and there are certain codes. This is just a code snippet of the kind of thing you would do in your code just to see that you're using GPU devices. In general, your GPU execution is going to just be a lot faster than a CPU. It's going to grow more linearly, whereas a CPU execution time is going to grow non-linearly as you start increasing the number of layers. So GPUs, they scale really well. So the GPU is always faster, but it might not necessarily be the thing you want to do because you're typically waiting more in the job queue. And there's some memory limits. So if you have memory limits, then you have to, if your model's too big, your data's too big, you have to load the data in batches. So you have to do some more coding in those cases. So that's the trade-off. All right. Before we get to, I think this has got to be on the last slide. Oh, okay. So find relevant examples for your domain. A task, that's always a good thing to start with. TensorFlow is pretty good documentation. They have a lot of examples. In fact, I find that a lot of people have blogs these days on deep learning. You can find so much blog information out there, and some of these websites are pretty good. a lot of them will take the tutorial information that's in Keras and just maybe change a little bit and then put a blog on it, write a blog on it. So I think, really, it's good to look at the Keras examples, the Keras tutorials, and then I kind of start with those and then go to maybe some of these like other websites. Okay. All right. So let's go to our exercise. Let me preview the exercise. We're gonna look at the Hypertuner notebook and play around with the parameters, setting up parameters for a Hypertuner search. All right, let me switch screens. All right, so this was my MNIST. I'm going to close that. And I have a Hypertuner notebook and a Hypertuner with solution notebook. I think we have time to, let's go ahead and open up the Hypertuner notebook. I'm just going to review it real quick. Again, we're setting up the build model and the build model hyperparameter functions. That's going to be the gist of this exercise, so that we get comfortable thinking about how do we build those models, how do we build hyperparameter searching. We'll run the notebook and we'll look at the hyperparameter results. And then we'll go through. We'll think about that too, because I'll show you how I get to how we summarize the outputs in this example. Okay, so this is actually, I think it's set up to run. It'll run auto. Let me go ahead and start running these cells. So the first cell is a bunch of import statements. I'm importing a Keras tuner as KT. I'm loading the data. This is just like the previous exercise. I'm loading my MNIST data. Okay, now I'm introducing a new function for the Hypertuner that wraps around the build model function. Okay, so for my first, so just right now, I'm just going to run through the model. Oops, okay, so I do have parameters in here. All right, so what I'm asking you is to look at this build model HP function. I've set up number of filters as one of the hyperparameter searches. And I'm asking you to set up a hyperparameter search for activation, where the choices are going to be two different values. So we're going to fill in the values, and we're creating a choice kind of search. So it's like a discrete choice. We are giving it a name. So the hyperparameter object will know it as HP activation. My code will get the choice as a variable called HP underscore activation. Okay, and then what I'm going to use, for this function is going to return, it's going to call the build function that we did before. So the build function we did before is in the next cell, except here I have the number of filters as a parameter, and I want to add a parameter. And I'm going to call it, we got to give it a name. Okay, so let's call it activation to use. And I'm asking you guys to fill in the rest of this function so that it uses that parameter. And there. So take a look at this code. Take a look at, we have some time. I think we're going to go till like 10:15 and then take a break. So go ahead, take your time. Look at, again, if you open up these links, you'll see what the options look like for these functions. I'm asking you, let's see, fill in code. Okay. Oh, so we're looking at the parameter values we want to look at is ReLU or ELU. So we want to run the MNIST problem with those two different activation functions and make sure those activation functions get used when we're actually building the model. The hyperparameter, the hyperband function, again, this is all set up for you guys to run. We'll go through this in a little bit more detail as we run it. But this has a lot of options that control how the tournament's going to play out. Actually, not that many options. There's only 2 or 3 options. And then we're going to get output like this. So go ahead and make the changes in those functions, and we'll go through the rest of this in a few minutes. I'll give you guys, let's say 5 minutes, and then we'll start going through it together. Okay. So I hope everyone has a chance to think about what's going on here. I'm going to go ahead and start just filling in some of the blanks and then run it. And then we can spend time looking at the output, because really probably the more interesting, maybe not interesting thing, but the harder, there's some harder questions that come when you run in networks and you run, even if I run this nice, this tool, it's not always obvious, that you have how you interpret the output or how you want to go from there. Okay, so this first function, again, it's a build model with the hyperparameter object. I'm defining my choices for the possible hyperparameter values. The first one was an integer with a minimum and a maximum value and a step size. This one, I'm going to give it a ReLU as one possible choice, and the LU as another choice. And if we had time, you could even stick in the leaky ReLU or something else. So I'm only using 2 choices. Typically, you're gonna, I think you're gonna be using more. I don't have, for example, number of layers. That would be an obvious one to do next, maybe. I have to make sure when I run this, when I run the build model, I'm going to make sure I pass it this choice as a parameter. So my HP underscore number filters, HP underscore activation are going to be passed into the build model function. I've set up the build model function to use the number filters and another parameter called activation to use. So that's what I have to use. I have to take the activation to use variable and fill in these blanks. Notice these first 2 layers are convolution layers. And if you remember, I said that the rectified linear unit, the ReLU, and its variations are good for convolution. They help us build deeper layers. They mitigate that vanishing gradient problem. They're nice and quick to calculate. But I also have it here in the dense layer. And maybe in the dense layer I want to try something different. So here I'm using the same activation for all 3 layers. Maybe you want to try something a sigmoid in that classification layer. There's no reason. So, but again, it's another kind of choice you might have. Let's see. I've set this up for categorical cross entropy. I've already got the atom optimizer there. So I can run, let's see, did I run, let's see, make sure I run this. I run both those cells. Now in this hyperband tuner object, when I set that up, I have these parameters, which are kind of again, this tuner object is going to wrap around the fit function. The first parameter is the function for getting the hyperparameter choices. You tell it what the objective is, max epochs. So your max epochs, it's not the same as number of epochs, right? So when I was fitting a function, I said, oh, use this number of epochs. Here I'm saying, well, you want to set up a number that would be the most epochs that you think you need to find a good fit. So it has to be high enough so that if you train any one model with some particular network configuration, it's going to be enough. So you always want to use this, make this a little bit higher than what you think you need. The factor is 3, and that's the default value from Hyperband, and that's really related to like the branching size of the tournament. So you're always, 3 means you're pretty much taking your total number of possible configurations and splitting it up into like a bracket of 2 at a time, like if it was a competition. Hyperband iteration. So you can run through this whole thing a few times. So the more parameters you have, the more you're going to want different iterations, so that it can, try out different parameters with different seeds and maybe get slightly different winners and losers as it builds the number of epochs. One thing to keep in mind, Hyperband, when it runs, it saves all this information. You can just create a new directory every time, or just create one directory. This example, I'm going to create a directory called Hyperband test. It's going to come up with it's going to save all the information there. And I'm just going to every time I run this, I'll just overwrite it. Executions per trial. So if you run neural networks enough, you know that sometimes the random seed can slightly affect which, it's going to impact how the weights were randomized in the beginning, in the initialization steps. And so you might want to run this a few times just to get a better sense of what the performance is for any one network configuration. And that's what this execution per trial is. But let's go ahead and run this. Okay, and as it runs, it says, okay, assemble the model. It's training for 3 epochs. Oops. And it runs a second trial. So it runs a trial, comes up with an accuracy value. Then it runs a second trial, and it says, well, okay, this is my best value so far. It tells you what the hyperparameters are. And it just keeps running trials. And it's changing, should be changing these. It tells you what the best values are. Okay, so in this example, it's running with 20 filters, a different activation. And it's running each of this first part with only 3 epochs. But as it runs, it'll reload some of that information. Now you can also go, let me show you this. We can go into, if you go into the directory where we have this notebook, okay. So on my shell, that's it logged into Expanse. I have the Summer Institute. This is 5.1b Deep Learning, Part 1. Intro to Deep Learning is the folder. And I have this subdirectory called my HP trials. Now, where did I specify? I specified my HP trials somewhere. Oh, there it is. Directory name, my HP trials. So that was a parameter for the Hyperband object. Here's my project name. So so far it's run 8 trials. see what those files look like. And every time it runs a trial, it sets up a checkpoint and some information about the trial. So that information actually is there and it's available for you to review. That's what we're going to show in the next couple coding cells. This kind of information about what was the trial, what were the parameters. If you're good at reading JSON, you can almost read this. It's a little bit readable, but we don't have to read it. But I just wanted to point out that that's what's going on behind the scenes. Now it's run 10 trials, or actually 11 trials. If we go back to our notebook, let's see, there it is. It's still running some trial on some different network configurations. So it's going to take a little while. It's running through different sets of parameter values. Did it finish? No? Okay. 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 So when it finishes, I print out the result summary. Let's see what else. Oh, okay. I printed out the result summary, and then I have a little function here to just get the best hyperparameters for 5 trials. All right, so here's the result summary. It gives me what my best validation accuracy was. No, trial 13 complete. Oh, here it is, best value so far. Okay, so that's the best value so far. And then it's showing me the 5 best trials. And if you want to, you could look at this. We could go through this sort of in more detail. How many filters, what the activation was, and it gives you the score. So in this example, my ReLUs were all in the top 5. And here I have a little loop just to get one score, one set of parameters at a time. Let's see. And so my best 5 configurations are right here, from 0 to 4. The best one was 32 filters using ReLU. They were all using ReLU, by the way. So that seems really interesting, considering the fact that the recommendation for that book was, or the suggestion, I should say, from the book was that ELU is better than ReLU. All right. So this is the kind of thing you can play around with. As you see, it's going to take a little bit of a while to run. I find that it will save you some searching. Once you have an idea of where your good parameters are, it doesn't necessarily save you that much at that point, because then you can just run a grid search, and as you can see, this takes a little bit of time. But you could do a grid search and almost get the same kind of configuration values as your optimal. All right. All right, and then there's some other information, getting to brackets, getting the best, which was the best trial. If you run this again, you might get slightly different answers. All right, so you might try that. Run it 2 times in a row and see if you get the same answers. Again, if you look at the actual error, if you look at the actual scores, you're not finding a huge difference between, let's say, all right, that was the trial summary. You're not necessarily going to find a huge difference between these scores. So, this is an accuracy in the 3rd significant digit. But it's there. There's something there. Okay. Actually, I have to rerun this. Wait, there we go. I forgot I did. That was an old run. All right. If you run it again, yeah, so you'll get, see here I got slightly different values from the previous time. I ran this last night and I have slightly different values. Okay. Any questions on that? Okay, someone asked, hypertuning doesn't seem to have made too much difference in this case. Remember, this is a pretty simple problem, the NS classification. So I do find that, you know, the difference between, let's say, using 3 layers and with 30 units versus 3 layers with 40 units, you're not going to, for a lot of problems, you're not going to find a big difference. And so what I do find, though, that if you run it enough times, you will find that, gee, you know, maybe 2 layers tend to do better more often than 3 layers. So for any one execution, maybe 3 layers will come out as being like a better configuration. But over, you know, if you do this several times, I think, you know, you'll find more, like after a while, maybe you'll find 2 layers are better more often, for example. So in this case, it's a kind of a simple problem. I think that's true for, I think for any problem, if you don't change your hyperparameters much, it's probably going to be the same kind of thing. You're not necessarily going to find a big difference. The more you change your hyperparameters, the more you'll see, like, oh, okay, maybe it does make a difference. So in fact, if we go back, let's see, I'm see if I can find the. Let's try this. Let's just do a ReLU. Okay, so this should run a lot faster. We'll do a number of filters where the minimum value is 2. Now for classifying 10 digits, I'm pretty sure, in fact, I'll even just do, well, let's leave it at 2. I would think that 2 filters may not be enough. We should find some differences in performance. So let's do this as an experiment. I'm going to say kernel restart all cells, restart kernel and run all cells. Now in this search, because I'm only doing 2, 4, 6, 8, 10, 5 different filters, 1 activation, I only have 5 possible configurations. So, so hopefully this will run much quicker. But that's a good question. You know, it's worth kind of exploring this kind of thing. You know, when does hyperband? In fact, it's kind of one of the active areas of I think of research right now is finding really good hyperparameter search tools. You know, there's some, you know, some people say the Bayesian optimization is better, but it takes time. I mean, it's almost like, well, you know, part of the problem is it's a discrete space. Going from 2 layers to 3 layers is a discrete jump. So you can't do gradient descent over, let's say, number of layer variables. All right, I think it just ran. All right, look at that. So the best parameters are in exact order. The best parameters go from 10 to 2. And if we look at the values, we see that 2 filters really perform noticeably less. It's a much stronger difference than 4 filters. But the difference between 4 and 6 is smaller. The difference between 6 and 8 is also smaller, and the difference between 8 and 10 is actually noticeable. Let's try running this again. I'm gonna go up here. I'm gonna change the seed. Okay, so it's running. Let's try an 8 filters. Now it's trying 10. Okay, so I ran it again, and now look what happened. 8 and 10 switched. 6, 4, 2 are still the 3 worst. So, you know, if we did this over and over again, would 10 and 8, you know, maybe they're going to trade places as to being the best one. Maybe I should throw in like 12. Maybe I should be separating these more, like try 2, 2, 4, 8, 16. Maybe I should do like an exponentially growing number of filters to get a better sense of the space. But you can see the ones that do worse stay worse in this short little test I did. And that kind of makes sense. 2 filters probably isn't enough for 10 classes. Not that it's never going to work, but it's just not, you know, not optimal. Clearly not optimal. So I kind of think that this kind of tool helps you at least get a sense of what's bad, what's, you know, where you don't want to, you know, what kind of parameters aren't near the optimal configuration, and what kind of parameters at least are competing. Does that make sense? I hope that answers that question. But otherwise, we'll take a break till 10:45, and Mai will talk about layers, right, Mai?
Yep, that's right. Sounds good. Layers, deep learning layers and architectures.